In engineering, we have a transducer that measures some physical quantity, and that transducer typically outputs an electrical signal, either current or voltage. And then that voltage is read in by a computer or something else. But the point is that there are transducers, electrical transducers, all over the place, and we need to be able to read their output. So we're going to look at measuring voltage briefly, and then go on to actually inputting that voltage into our measurement system. To begin, consider a charged particle of charge Q that is in the presence of an electric field E, and the particle is moving with a velocity v, and it's in the presence of a magnetic field B. In such a case, that charge experiences a force magnitude F. Well, these are vectors, the bold quantities, so it's magnitude and direction F. If we differentiate this along the path S, then we come up with this expression, and we want to use this relationship in a meaningful way, and so we're going to use it in a system where there's no electric field. So you can see here we have current flowing through a wire in the presence of a magnetic field. And we're going to make a couple of assumptions. Well, we're just going to assume that the wire is perpendicular to the magnetic field. So if we integrate this expression over the length of the wire, then we come up with a value for the force experienced by the wire. And that force, this principle, is what allows us to measure current. So we can connect this wire to a spring, measure the deflection of the spring, and that is a measurement of the current, if we know the stiffness of the spring, because current is related to the force. And similarly, if we have a known resistance connected to this wire, then if we know the current going through that wire, then that enables us to measure the voltage from one end to the other. So again, we want to measure voltage from one end of the wire to the other. If we have a known resistance, then we can determine the voltage by multiplying the current that we measure from the deflection by that known resistance, and that will give us the voltage. What we just looked at was an example of an analog meter, and they measure current. That's where they start. And like I said, you could go measure other things from that. So if you have, for example, a known resistance, and you can measure voltage using the same meter. And then digital meters, they inherently measure voltage. And the way that works is the digital meter compares the measured voltage to the output of a voltage supply. And that voltage supply goes from full scale, say 10 volts, to 0 at a fixed rate. And the voltmeter is regularly comparing the voltage source value to the measured voltage, and when they're equal, then the time that it took to reach that point gives the voltage, because the voltage source was changing at a known rate. The point really being that analog meters inherently measure current, and digital meters inherently measure voltage. So again, you could use a digital meter to measure current if you have a known resistance, etc. Now, whenever we have a transducer, the output of the transducer needs to be input into our system. Our system being where we process the signal, maybe record the signal, etc. And there are loading issues whenever we input that voltage. Loading issues meaning that our system can change the voltage of the transducer. So it could alter the output voltage. And we want to take steps to mitigate that effect. Here is an example where we are using a voltage divider circuit to observe the change in resistance. This is a 3-terminal device where we have a changing resistance based on a physical quantity. And if we connect it to a power supply, then we can measure the voltage from the moving terminal and get a measurement for the physical quantity. Now, our voltmeter is going to have some resistance, Ri. And if Ri was infinite, then we would have a linear relationship between the output voltage and the resistance R. The ratio, according to this voltage divider, would be that E over R is equal to E0 over Rm. Now that's for an almost infinite R sub I. In reality, there's going to be some current going through R sub I, and it will change the voltage E. And in that case, we get this expression for the ratio E over E0. And here is a plot for E over E0 as R changes. So as R goes from 0 all the way up to, as R over Rm goes from 0 up to 1, then you get these curves for E over E0. And you can see the curves vary depending on the ratio Ri over Rm. Whenever Ri is small, it's highly nonlinear, and as Ri gets bigger and bigger, it becomes more linear. So we'd like to have a linear response. For example, if we're measuring voltage, we don't want to have a really low sensitivity and then it all of a sudden spike. You know, a small change or big changes make no difference in our measurement until all of a sudden small changes make a huge difference. And here's that ratio, E over E0, and we want to see what happens as Ri goes to infinity. Looking at this ratio here, you see that as Ri goes to infinity, then E becomes linear. E over E0 becomes linear. And these are examples of loading effects. So whenever we have a transducer, we don't want the measurement system to influence the reading of the transducer. I said transistor, but I meant transducer. So we need to take into account non-ideal input circuitry. And if we want to see how much the real measurement, E over E0, is going to differ from the ideal case where we have an infinite resistor, or then we can look at the fractional loading error. And one thing that we'll notice, and it's also shown in this plot, is that at the ends of the scale, when R becomes either 0 or equal to Rm, then the fractional loading error goes to 0. So the effect of the voltmeter resistance, non-infinite resistance, becomes less and less as we get closer to the ends of the scale here.